Okay, continuing, we had discussed the first entry, OSPF entry, which is the neighbor table. After we've exchanged my hello packets, takuziva who is our neighbor, and the neighbor table displays who is our neighbor. Second entry, we have the LSDB, which displays all routers in the network. Why it's able to do that is because the LSDB basically is the map or topology of the network when synchronized. Our last entry, obviously the routing table. After LSDB comes SPF calculation. SPF calculation gives us the routing table. So from the link state database to get SPF calculation, we get the forwarding database. This is from the forwarding database. Forward. So number one, it was the adjacency database. Number two, link state database. This one for forwarding database. So from the forwarding database, that's where we get our routing table. And the routing table displays routes which are generated after the SPF algorithm has done its job on the link state database. My routes and from routing table are the routes which will be used to get to specific networks in our network. How do you display a routing table? Huawei devices, we use display OSPF routing. Cisco, we use show IP route. And voila, these are the routes in our network. So in short, three entries that we have. After exchange of hello packets, we have the adjacency database, which will give us the neighbor table. After exchange of database description, we have the LSDB, which will give us the LSDB table. In Cisco, I think it is called the topology table. This one here, it's called LSDB table. Okay, link state database table. This is also called the topology table. It shows us the topology of the network. Then after my LSDBs have been fully synchronized, let's just say after SPF this time, no packets exchange here. It's just SPF algorithm calculation. We now have the forwarding database, which will give us the routing table. Working mechanism. Some of the information now is probably going to sound repetitive. Like we're going to talk exchange of hello packets, neighbor relationship, exchange of DD packets, link state database, SPF calculation, forwarding database. That's where the routing table comes from. That sort of basically describes the working concept, working mechanism of OSPF. Here, we'll repeat the same thing. Relationships between OSPF routers. We have two important concepts about the relationships between OSPF routers, neighbor relationship and adjacency. The difference, when we talk of neighbor relationship, that's where we talk of exchange of hello packets. Neighbor relationship. R1 knows R2, R2 knows R1. That is what we call neighbor relationship. Neighbor adjacency, on the other hand, is after LSDBs fully synchronized. So when we talk of adjacency, it means we have fully synchronized our databases. Yellow packets atopera kudhara, DD asendwa, LSAs, LSRs, LSAs asendwa ese, LSDBs edu they are synchronized. That's where we talk of adjacency. On a simple network, two routers are directly connected, exchange of yellow packets. That's a relationship. Then when LSDBs are synchronized, that's where we talk of adjacency. Process of establishing a relationship. Here we have a summary of how a relationship will. Process of establishing an OSPF adjacency relationship. Now they're using adjacency relationship in the same sentence. This is how adjacency, this is how we get to adjacency, fully synchronized LSDBs. Number one, hello packets. We establish a bidirectional neighbor relationship. Number two, this is election of DR and BDRs. Negotiate master slave status. We'll get through that, I think, in the next slide. Number three, this is exchange of DDs. Mutually describe the LSDB. Then number four, if DDs are compared, missing information is updated by LSAs. Then our LSDB synchronized, and from there, we have step number five, where routes are being calculated. Information will sound repetitive, but hopefully, don't understand. Step number one. Step number one here, that's where we have exchange of my hello packets. With that, we define, how do we define those? Stages. Let's just say stages. We define stages between our step number one. We have a stage, a state, not stage. Let's define my states. Within our steps, that will define among my states. Although it's repetitive, I think every level to nodibisa bichana. Tapa tichitaura exchange of hello packets. Panotanga exchange of my hello packets, we have what we call the initialization state. Before this one, excuse me, we have the down state. I don't know if it's there in Huawei, but it's there in networking general. Before any exchange of hello packets, we have the down state. So router E down state, it means it is not exchange any hello packets. That's the down state. The moment we start exchanging hello packets, we have the initialization state. So R1 is initialized, it is in init state. This one also initializes, it is in init state. Mapackets here can exchange one. Init state here doing appear. So yellow packet render oak. It means R2 now knows R1. Yellow packet render oak. It now means R1 knows R2. Do knows init state. If I then send another packet, yellow packet, to R1, kunok information R2 yatoko kudara. That step inenge yakunzi two-way. It means we've already discovered R1 or R2 on the other end. We now have what we call the two-way state. With the two-way state, that's where the election comes in. Election, here designated router, election, here backup designated router, with all other routers becoming DR others. So with the two-way state, we have a router receiving another hello packet. However, in its database, in its the adjacency database, the neighbor is already there. That's what we call the two-way state. Its importance in two-way state is usually by election process. let's just say election process. Up and open to election in the two-way state. After the two-way state, it means we've established bidirectional communication. We now go to exchange of DDs, exchange of database descriptions. Panotanga exchange R1 in this case, the exchange start. Then pano exchange go from R2 in exchange. Am I putting this in order? Panotanga exchange wa R1 going to R2, that's the start of our exchange. Then for this one, that's another exchange. This another exchange. We are exchanging my databases. My databases edu, they will get compared. Kana compare wa ndo panazopinda my request name advertisement. My state edu here, we have the exchange start and the exchange. Exchange start is the beginning of our exchange. Exchange is when we have exchanged all database descriptions between my routers edu R1 and R2. In this case, however, multiple exchanges are right one. So you can see we have exchange X, then we have exchange X plus 1. I cannot see it. We have exchange Y, then we have exchange Y plus 1. I think this should be X plus 1. Which one? This is X, this is Y. This should be X plus 1, this one. And I'm not sure why it's Y. X plus 1. So we have multiple exchanges that we have here. But in short, we define these states: exchange start and exchange. Exchange start is the beginning of our exchanging of database description. Then exchange, after we've started, we exchange more DDs up until we have all databases exchanged between our routers. Database descriptions, not databases. Database descriptions exchanged between all our routers. From there, compare my database edu. Can I compare if there is something missing, we request. But no requester, tinenge tapa state inozi loading. Tika requester, we get an update in LSU. An LSU is made up of a number of LSAs. We acknowledge LSU edu. If there is anything else missing, we send another LSR. We get an LSU, we acknowledge up until everything is synchronized. If our LSDPs are synchronized, state the full state. Then kana tapinda full state. After this, the SPF algorithm. So in short, my states edu they go like this. Downstate. If I exchange my hello packets, ndakupinda mu initialization state. If I exchange my hello packets, ndakupinda mu two-way state. If I exchange my database description, if I exchange my database description, ndakupinda mu start of exchange. Exchange start. If I exchange more database descriptions, time exchange. If I exchange my LSRs, my LSUs, my LS acknowledgements, time loading state. Then after loading state, synchronization, time full state. After full state, SPF algorithm, apa ndo pane routing table header. Working mechanism of OSPF. Review of OSPF neighbor table. What does the OSPF neighbor table show us? Some of the important information that we're gonna here we have, obviously, route IDs. The neighbor table shows us this is for R1, this is for R1. So it will show us my neighbor is this one. Neighbors, this one. It shows me the router ID of the neighbor. Information in my neighbor table here. It also show me the address of the neighbor interface 10112. It will also show me the state where I am, the state the router is currently is with its neighbor. In this case, it is in full state. Can I remove full state? It means those two routers are fully synchronized. It means my LSDBs, they are fully synchronized. That's the state we are in. Is another important information in report, priority value. Priority here is at 1 here. We have also information a designated router. I think we'll define and go a bit deeper designated router and backup designated router. We have also information about dead timers. Do we have yellow timer by now? I cannot see it. We have dead timer. I think that is well important. So I think important information which is this being displayed here, you need to recognize is router ID of the neighbor, address of the interface of the neighbor, the state, then which is our designated router. Right. OSPF network types. We have a number of types of networks that we have. Number one, we have what we call a broadcast OSPF network. We have what we call a non-broadcast multiple access. Non-broadcast multiple access network. We have a point to multi-point network and we have a point to point network. Type of networks where they behave differently with respect to OSPF. Number one, point to point. What defines a point to point? It's a network where we have a direct link between two routers. Information ikabva pa-interface apa iri kuenda pa-interface iri. So it's a direct link, point to point. Point to multi-point. Information ikabva apa inokwanisa kusvika panapa, inokwanisa kusvika panapa. That is not a point to point. That is a point to multi-point. Very simple. So depending on the type of encapsulation that you shandisa at layer 2. For example, triple P. That's a point-to-point protocol there. It defines a point-to-point link. The type of OSPF that we use here is different from the type of OSPF that is being used there. In this case, we do not have DR, backup DR elections. Is this not the right time to define DR? It's defined after. Let's just define it now because it's popping up everywhere. DR, PTR. When we talk of a designated router, it's a way, when you talk of designated routers, it's a way of centralizing how advertisements are flooded. In a network where I have multiple routers, for example, am I doing this right? So let's say I have router 1, router 2, router 3, router 4. All these routers will need to establish neighbor relationships. How many hello packets will be sent here? All these routers will need to synchronize, send database descriptions, flood LSAs. How many packets will be flooded? It will be a lot of packets being flooded. So instead of having that much traffic in a multi-access network like this one, we can have an election where we define a designated router. So instead of having my relationships being between 1 and 2, there's a relationship needed. Between these ones, relationship. Between these two, relationship. Another relationship here. Then relationship here R3 and R2. Then relationship here R4 and R1. That's approximately 6 relationships. Instead of having those, if I'm using a designated router, everything is centralized to this router. So all my relationships now are only with router 1. So instead of having 6 relationships, if I'm correct, I'll only have a relationship of R3 with R2 with R1, this one with this, then lastly R4 with this one. 3 relationships. It means traffic yango is a bit less. That's the idea around having a designated route. Now, designated router, if there is need, you also flood my LSAs because the goal of my relationships, my neighbor relationships, is so that you can then share my database descriptions, then synchronize. But now that we are not having my relationships directly with each other, this central device, which is our DR, door shall link every other device in the network. So door no flood to everyone, this one. Everyone, every LSA will be flooded from that central device. So the idea behind a designated router is in a multi-access network where my packets edu can basically shut down network akawandisa. We now have sort of a central way of disseminating my LSAs instead of having everyone sharing their LSAs. So in a network, coming back to this one, in a network, in a point-to-point, there is no need a designated router here because information is up, and up. No need for a designated router in this one. Adjacency will only be with designated router instead of all other routers. Typical example, triple P link. When an interface uses triple P encapsulation, the default network OSPF is P2P. The way a network in a P2P is configured will be different to, for example, this one. So I think key takeaways from this one, on a point-to-point, there is no election. There is a direct link between two routers. Then we go to this one, broadcast multi-access network, BMA. This one, it allows multiple routers on the same segment to communicate. Multiple routers on the same segment to communicate. In this one, we have a DR election. It refers to an environment that allows multiple devices to access and supports broadcast. A typical example is an Ethernet network. When an interface uses Ethernet encapsulation, the default network type is OSPF interface. The default network type of the OSPF interface is BMA. So this one is a bit different from a point-to-point, because if I broadcast here, switch radio will broadcast to these ones. The issue here, traffic and router, it becomes a problem. That's why we need a DR here. So guys, a DR panel, this one will be responsible for flooding, and only this one. Kana receive DR here. Then pano flood, my LA says this one will flood, this one will flood, this one will also flood. So in a case of a broadcast multi-access, there will be need of the election process. Non-broadcast multiple access. So in this one, it is multiple access. However, there is no broadcast. An example, ndiyo frame relay. So ndikaenda kaisa switch panapa, ndikabvisa this frame relay. Iri ndiyo rinonzi multiple access, but with the broadcast. Switch rinokwanisa broadcast. This technology frame relay, it does not support my broadcast. However, it is still multi-access. Elections are required here as well. Elections are required here as well. Why? Because it is a multi-access network. We go to the point to multi-point. Yakada ufanana bichana ne point to point, but we now have multiple point to point links. One router connects to others in a point to point manner. So one router connects to multiple routers in a point to point manner. So there is a point to point between this one and this one. It also has another point to point with this one. We do not have an election here. So pano configure network yedu, we configure it sort of as a point to point. There will be no election process. The reason why we're having my type in my networks is so that we understand, can attack with the configurations the OSPF. You specify, is this a point-to-point network or is this a multi-access network? My multi-access network essay, you see they will require my elections. So we have my multi-access, then we have my point-to-point. Kuno conduct my elections. No elections. For my multi-access, we have ones which broadcast, then we have other ones which does not broadcast. For point-to-point, we have the point-to-point itself, and we have the point-to-multi-point. Those are the type of OSPF networks that we have. So where we can configure a multi-access network, oregera kuspecify kuti pachafanira kuitwa an election, network yako will be a problem nema-flooded LSAs. Background of DR and BDR, I think we've gone through this. Multi-access networks are classified as BMA and NBMA. Ethernet is typical. On MA networks, each router establishes adjacencies with all other routers. Excessive OSPF adjacencies exist on the network, increases the load and the number of OSPF packets flooded. Once the network topology changes, LS flooding on the network may waste bandwidth. What's the solution? Selecting one router. That router will be responsible for flooding LSAs, meaning we don't waste that much bandwidth. DR and BDR. To optimize relationships on MAs, OSPF specifies three types of routers: DR, BDR, and DR other. So, per network elections, one router becomes the DR, this one becomes the backup. This one will become the designated router. Every other router in the network becomes what we call a DR other. So my adjacencies, they are formed between my DR other and my designated routers. You will not see my adjacencies between this one. Ndokureduce load kwacho, basically. So pese panoitika flooding, hapana flooding yanoita. Flooding inobva from these designated routers. And that's how we do not waste bandwidth here. Their relationship is in the two-way state. State ye two-way, ndo panoitika election process yekuti designated router in the RIP and what becomes the DR others. OSPF domain and single area. I think I've passed through this. In area, OSPF domain consists of series of network devices. OSPF router floods LSA in the same area. Same area, it means LSDB is the same. Area 0, LSDB yepanap, yakafanana. If all LSDBs are the same, it means it is the same area basically. If there's only one OSPF area, number of OSPF routers increases with network scale. This causes the following problems. Kana ndine only one area, my routers akawanda. The problem is the LSDBs becomes larger. The size of the routing table increases. Larger router resources are consumed, device performance deteriorates, data forwarding is affected. I think we've touched on that. My routers akawanda. I think I touched from perspective of my calculations. The calculation yedu inenge yakakurisa static. It means processing pama routers edu will be a lot. The load will be a lot. So to solve that, that's why we have multiple areas where we segment my networks area basically. And those are multi-area OSPFs. With multi-area OSPFs, we have to define type of routers that we have. We have my internal routers. DOMA routers are within the same area. We also have my BR, backbone router. My backbone routers, DOMA routers, which are in the area 0. There is need of at least one backup router in there is need for at least one interface in for a backup router. So iri backup router is all its interfaces are in area 0. That's a backup router. IR internal router, all its interfaces are in the same area. So this is an IR. This is also an IR, but also a backup kana, a backbone, I mean. Backbone router kana rem area 0. Apana area 0 and let's just call this one area 0. That's why I'm a backbone router. Then we have in ABR. ABR, that's the router linka ma areas. So this one is an ABR. This one is also an ABR because it's linking these two areas. It's linking these two areas. That's what we call an area border router. Then an AS boundary router, ASBR, is a router which links areas with different routing protocols. So kunoko kana kune area rine OSPF, kunoko kune another routing protocol, another AS, OSPF. What's another protocol in AS? I'm forgetting another protocol. Let's just say routing protocol, which is different from this one. I didn't want to use RIP, IGP. Other types of IGPs we have. Hi, I'm flooded. So if we have two protocols which are different here, what connects and redistribute routes between them? Ndoma ASBR routers are ASBR routers. Kana ma-protocols are the same. In this case, rinenge richingonzi an area border router. Those are the type of routers that now, I think, simple here. Typical OSP of single area and multi-area network. So this is a single area 0, backbone. Here we have area 0, area 1, area 2. So you can see I am my border routers are these ones. This one also border. This one also border. This one is backbone router. We can define the type of routers that we have. Typical OSPF configurations. This is where we end. Our configurations, we're going to start. Then I install an ENSP. I think I'll task you to do that. It's a bit complex. In Ansanadombo is a ENSP. It's a bit complex because it lacks my updates. It's very unfortunate. It lacks my updates. So when I'm on Windows 11, it becomes very difficult to install ENSP, but we'll find ways. And with that, I think I can conclude this one. Any questions before I end this? Can I report type of networks and share? Any questions whilst I look at this? I was looking for this protocol. ISIS. But if you do not have any questions, thank you very much for attending this session. Let's work, let's push. End of February, everyone will be writing their exams, I think.